these because a lot of people out there don't know how to use them properly. So we're going to kick it off with the very basics. And if you don't know what an LED is one of these things. Okay, it's a little lamp. And LED stands for light-emitting diode. First one. And believe it or not, it's called light-emitting diode because it is one of these. It is virtually a diode. Okay, the only difference between an LED and one of these, okay, an LED and a diode, is that an LED emits light. Fundamentally, you know, it's the same thing. Okay, it's a diode, and it operates more or less the same way. But there are a few dissimilarities. So, first up, we're going to go through a couple of the things that make LEDs different from standard diodes. First of all, it's the symbol. Your standard diode is that symbol. Okay, anode, cathode. You can say plus, minus, positive, negative. If you like to think about it, the arrow is the direction of current, so it flows in that direction. If you can't be asked remembering anodes and cathodes, it's forward biasing that direction. Again, it's the arrow. Diodes only conduct forwards, not in reverse, hence the big bar telling you that it's blocking it, and the arrow again, the little triangle symbol. And you can even think of it as in and out, if you like. Now, the only thing that distinguishes, you know, your standard diode symbol from an LED one are two little arrows pointing outwards at an angle, just denoting that it emits light. Okay, that's the only difference between in the symbol. The other difference is, obviously, an LED emits light. Yeah, that's a big difference. Apart from that, it's just a matter of numbers. So, they both have forward and reverse characteristics. Okay, they only, issue note, they only conduct currents in forward. They don't operate in reverse. So they are polarized. The only difference is the values of that. Now, standard silicon diode, 0.7 volts. Okay, you need to bias it with 0.7 volts before it starts conducting any current, or but it's you know, efficiently conducts current, because you can get it conducting a bit lower, but let's not be too anal about it. 0.7 volts, it operates perfectly fine. LEDs, on the other hand, because they emit light, and the way how they emit light is we chuck a load of impurities at them to turn them into a very crappy diode. Their forward bias characteristics are a lot higher. Okay, typically anywhere from, depending on the colour, which I will flash up here. There we go. So depending on the colour, you have different forward voltages. Okay, it could be anywhere from, I don't know, 1.5 volts, 1.6 volts to all the way up to, say, 4 volts, depending on the colour and the chemistry inside them to actually make the different colours. Now, there's loads of different types. You can get white LEDs, red LEDs, blue LEDs, green ones, infrareds, UVs, you name it. If the colour exists, you can get it in an LED nowadays. The other difference is currents. Currents are very important in LEDs because they are easy to destroy. Just like you have a forward voltage, you also have a forward current, your maximum currents. That can vary hugely. I've seen LEDs which operate and light up, say, from, I don't know, just a couple of millivolts, which would be fine for surface mount ones, to the 5mm ones, and the more powerful ones which go up to hundreds of millivolts. So your current consumption can be quite high, but downside lower than incandescent or halogen or anything like that. They are really efficient compared to those lamps. The only other difference really between this and a standard diode is numbers again, and that's in reverse bias characteristics. The reverse breakdown, a point to no return, you take it over that value in reverse and you will destroy your diode. LEDs compared to diodes are extremely small. Standard diodes, or standard diodes, maybe 40-50 volts and up in reverse before you actually destroy them. Rectifier diodes, downside higher barrier diodes and shocky diodes and all these other things, all these other diodes, okay, they all have a lot higher than these, because these will actually in reverse they'll break down within a few volts. Okay, you can get a red LED, you can destroy a red LED with just 5 volts in reverse. So be careful when you're connecting these up. Connect it around the wrong way, and if you do have a high potential that you drop across them, you can in actual fact destroy them, so be careful. Apart from that, they are virtually the same. Now then, how do you know which way around to connect an LED? Because it is a polarized device. It does have an anode and a cathode like a normal diode. On a normal diode, if you can see that, let's go in close, you can see a little black marking at one end. Denotes the cathode. So your band on a normal diode denotes the cathode. Yeah, pretty simple, pretty straightforward. You can see it is visible, hugely visible. LEDs on the other hand are slightly different. Normally a LED has a flat side to it. If it's a round LED like this, it has a flat side. Not always the case, because this one, as you can see, it doesn't have that flat side, whereas this LED does. Okay, you can just about, if I spin it around maybe, can you see it? It's difficult to see. You have to take it from me at the moment. I'll try and line it up. There you go, you can just about see it there. You've got a flat side and you've got a side that sticks out. It's got a ring at the bottom. This one doesn't have the ring at the bottom, if you can see that, and consequently it doesn't have a flat side. The flat side, generally speaking, on your LEDs is your cathode. Another one, which it could be, is the lead length. The longer the lead is normally the anode. Don't always trust that though. Those it is getting a little bit blurred, those lines are, and I have had the leads actually swapped around, so it's not always a good one to go for. Also, if you're salvaging LEDs, your legs will be chopped off, you won't know, so go with a flat side. The other way to distinguish between what's the anode and cathode is to actually look at the internal structure of your LED. Now, if it's a clear lens like one of these, okay, you can actually see internal. Can't really see it too clearly there, but I do have an image of this, which I'm going to flash up now, and I'm going to run you through it. So, as you can see from this image, we've got our LED. Our two legs are longer than each other. You can see that clearly, but we're interested in internal. What you can see internally to this, if you follow the legs up, okay, it's a little bit off at the moment because the actual lens is doing some funky stuff to the actual die. The actual internals is making them look a little bit offset. So it's a curved shape. Okay, can't really get away from that. Anyways, if you follow the legs up, take a look at the shape at the top. On the right hand side you've got a very small piece of metal rising, and on the left hand side you've got a very large piece of metal coming up from the bottom of the case. These two lumps are not, well, they are connected together, kind of. I'll come to that later. They're called anchors. Called anchors for a reason, is to anchor the actual lead into the epoxy housing, solely to stop you from yanking the leads out and disturbing the actual diode internal to your LED. The LED, if you can see this, a cup just in the middle, that is what contains your actual diode itself, your LED. That is what emits. The cup is a reflector that reflects the light upwards and out the top of the LED, which is why they're very directional. Inside that is your little p-n junction, which is then connected, okay, between these two metal anchors. Now, the large anchor where the cup is, this is generally the cathode. On the opposite side, there's a little bit of wire just joining your sample over to the anode. Okay, so you've got your little diode with your anode and cathode on it, in this little cup. Cathode is connected to the large piece, the anode is connected with a little bit of wire going over to the very small anchor down to your anode. So in this case, the cathode is the short wire, the anode is the long wire, the long lead. So that's internal to your LED. They're called anchors. Anchors anchor things in place, just like on a ship or on a boat. Okay, stops your little LED getting shifted about inside the case, getting damaged, getting moved, or anything like that. So any movement on a cable isn't really affected by internals of your LEDs. And yeah, something similar to that is what goes on chips, on ICs. You've got your pins coming out of your IC, and they'll all be anchored internals. Something similar to that. Anyways, that's the internal structure. So your LED is just that little cup just in the center, and that majority of that cup is just a reflector. And so yeah, that's it. That's where your diode sits. Right, I'm back. So how do you control these? Well, you do it exactly the same way as you would a diode, really. But it depends on the situation which you're in. And this is where Goldilocks and Three Bears come in. So, don't tell me I'm coming down with another cold. I got a right itchy nose this morning. So, yeah, just like Goldilocks and Three Bears, you've got three scenarios what Goldilocks was in. Okay. When she broke into the bear's house, she found their food on the table, all nice and cooked up, ready to eat, and bears have buggered off that. Well, they're being a little bit stupid. They should have used an alarm on the door, okay, or at least locked the door. Anyway, Goldilocks managed to get hold of their grub, and she found out that only one of the bowls was any use to her. Okay, it was just right. The other one was too hot. The other one was too cold. And she had a fill and then buggered off. Okay, all was well until the bears got home, obviously, but we'll leave out that part. Anyway, LEDs are exactly the same thing. There's only one condition which they will actually light up, and that's if you have the correct current and voltage being supplied to it. That's pretty rare. The other two situations is if you've got too little current and voltage, power, too little power, your LED doesn't light up, or it doesn't light up particularly bright. Third option is if you've got too much power and you end up burning out your LED, or you run it so hard that you you reduce the lifespan of it quite severely, and in some cases it can be so dramatic that it only lasts a few seconds. So really, there's only one condition, and that's the just right situation. Now, the just right situation for an LED can be quite different between LEDs and between manufacturers, and between what LED you get out of the drawer and what batch it was made in and so on. So there is a big problem, okay, being in that situation of just having just right voltage, just right current is, let's face it, like getting blood out of a stone. It's almost impossible. It's a bloody mystery. Okay, take a red LED for example. You need say 1.8 volts to turn it on at 10 milliamps. Tell me, what battery can you connect that has 1.8 volts? Absolutely none. which means that you're going to use a 1.5 volt battery to turn it on. For example, if it's going to be in a torch, you're underrunning your LED. It's not going to be as bright as it should be, or it's not even going to turn on. White LEDs even worse. Okay, white LEDs need 3.5 volts to power with. If you underrun them, a nice white LED is generally for illumination. You're illuminating something like a spotlight or a light in a room or an overhead lamp or something, you know. Wrong voltage level is not going to light up jack shit. So it is quite important. It's very easy to underrun them, and sometimes you might have too much power, and you can end up overrunning your LEDs and end up burning them out pretty quickly. So yeah, let's go through the situations and this is how you get around those situations, to have just enough, not too little, not too much. If you've got too much, I'll show you how to get just enough, and if you've got too little, I'll show you how to get just the right amount of power. So then, first scenario, too much power. Okay, very common one to be in. Okay. Yeah, why is it that I say okay so many times? I don't know. Right, so we've got let's say a battery. Let's say it's a 9 volt battery connected to our LED. Right then, one scenario, okay, yeah, it doesn't have to be a 9 volt battery, it can be a supply from an op amp or a transistor or whatever part of your circuit. On a digital output, it could be 5 volts. Let's say it's 5 volts instead. 5 volts is coming from a TTL device or a microcontroller or something. 5 volts, which means that you're going to dump 5 volts across this LED. Now let's say this LED has a forward voltage of 1.8 volts and a forward current or a diode current ID of 10 milliamps. Okay, a typical one. This will be a typical red LED. Okay, something that you probably everyone you're familiar with. A red LED. It's coming from a 5 volts. 5 volt out from your microcontroller, something like your Arduino, for example. Well, all that you're going to do, if you connect up your LED directly to this 5 volts, you're going to drop 5 volts across it. Obviously, as forward voltage is only likes dropping 1.8 across it, you're forcing it to do 5, which means that you're going to destroy your LED. You destroy your LED, you're going to have maximum current flow, and you could end up taking out one of the ports of your Arduino if you're not careful. There's no current protection on it. So what do? How do we get around this problem? Well, you want 1.8 volts and it naturally drops 1.8 volts across it. Okay, this is natural drop. How do you get rid of that extra voltage? The most common component that we all use is this one, our resistor. Put a resistor in series with your LED, it will drop 1.8 volts across your diode, the rest will get dumped across your resistor. So if it's 5 volts, 1.8 minus 5 volts gives us 3.2 volts across our resistor. Brilliant, we've satisfied our voltage requirement. Next, we've got to satisfy our current requirement in order to get it illuminating properly. And this pen's running out, so I'm going to swap to a more chunky pen. It may not be as good, but there we go. Alright, so what about our current? We need 10 milliamps. Well, resistors resist the flow of current. Putting a too big a value, too little current flows is not going to turn on the LED. Putting a too little one, this is fully biased, it's going to pass maximum current. You could exceed the 10 milliamps and end up killing your LED. So this value is very, very important. How do we work it out? Well, it's Ohm's law, V equals IR. Okay, Mr. Ohm comes to the rescue. So we want 10 milliamps to flow through our LED and through our resistor and back to our negative. Okay, negative, positive. Got 10 amps flowing in the circuit. We have 3.2 volts across our resistor. We have 10 milliamps flowing through it. What is our R value? Okay, can easily work it out. So it will be 3.2 over 10 milliamps gives us our resistor value, which would be 320 ohms. Yeah, simple. It's not a lot to it. How many 10 milliamps in 3.2 is 320. So 320 ohm resistor. Is there such a thing as a 320 ohm resistor? If you go out and buy one, there might be. In my particular lab, I don't. I have closest value is 330 ohm. Yeah, perfectly fine to use. Brilliant. It's only 10 ohms off, it's close enough. Not a baddie. But if it's further out because you're using an 9-volt battery or a 7.5 volt supply, or I don't know, you might have a 2-volt supply or something like that. Who knows? You work it out just the same way. Now I'm going to say that I'm going to use my preferred value of 330 ohms. 330 ohms. Value resistor, so I'll need an R of 330 ohms. But it doesn't stop there, I'm afraid. We know the resistance value. What do resistors also have? They also have a power rating. So make sure that you work out how much power is dissipated in that resistor. Get a too low a power rating, you can burn out your resistor. Get a too high power rating, perfectly fine. Now in my lab, I've got resistors of 0.25 watts power rating. Is that enough? Right, back. Someone just wanted me knocking at my door. Anyways, power, yeah. Is a power rating of 0.25 watts sufficient for this? Well, power equals, that's dissipated from the resistor will be 3.2 volts multiplied by the current. Power equals VI. So 3.2 volts multiplied by 10 milliamps gives us a power of 0.032 watts, which is 32 milliwatts. 32 milliwatts of power. It can sustain 0.25 watts of power, so well within our power rating. That's what you need to go for. So if you needed to purchase a resistor, you need a 330 ohm or 320 ohm minimum, and something around, an eighth of a watt, 0.125 watts. You could even go lower if you really, really want to. So as you can see, the power dissipated in this resistor is bugger all. Everything is going into this LED. LED's really efficient, that's why. Even with your resistor in there dropping excess power, it's not too bad. But you have to remember, power will increase as your voltage drop across your resistor increases. So if you've got 9 volts in here, it's going to be, if this was 5 volts, it's going up to 9 volts, so it's almost 10, it's going to be almost double. So yeah, it'll be almost 64.64 watts, which is still well within. So brilliant, yeah. So that's how you do it. It's very, very simple. Next one, it gets a little bit more complicated if you've got too little power. So let's scrub this ball back. Right now, too little power, what you have to do is to use this little bit of power. So say if you've only got, say, 1 volt, and you want to power your LEDs, you want to turn on your LED, you've only got 1 volt, well, it's not really going to do jack crap to that. We'll take the same LED as we had in the previous example, 1.8, 10 milliamps, same one, and you want to turn that one on. What do? Well, easy is to set up your LED with a separate supply and then use that 1 volt input to control that larger supply. So choose your supply. Let's say I'm going to supply my LED with 9 volts. Okay, and it's basically you do the same circuit. The only difference is we use a transistor. You can use a FET if you want. I'm going to do this example with a little BJT to control the LED. How to use a transistor? Alright, well, we're going to use it as a switch, basically. We're going to saturate the transistor. We're going to have it turned on maximum. So we get maximum current flowing through our transistor. So here's our transistor. We're going to use a NPN transistor. And the equation for transistor is IC equals HFE multiplied by IB. IB is a current going into the base. IC is current flowing through the transistor. IC, and HFE is the current gain of the transistor. So basically we're amplifying the value of IB. In order to use this transistor and saturate it and everything, we need to work backwards, okay, because we know how much current we want, we know how much voltage we want, we know the voltage drops if we use a similar circuit to the previous one, so we just need to work out our IB. So the circuit will look like this. So before we just had LED and resistor in series, we still got that. So we've got our supply going into a resistor, going into our LED, and that goes down to our ground or 0. Okay, so we've got our resistor R, we've got our LED 0 volts, and let's say plus 9 volts. So let's work it all out, or we could say our plus 5 volts. If we wanted to, we'd do our plus 5 volts again. Now this is 1.8 volts, it's going to have 3.2 volts dropped across our LED if we assume that our transistor is fully turned on. So we'll have our 3.2 across the resistor, we've got 1.8 across the LED, we want 10 milliamps to flow, so it will be a 330 ohm resistor again. No difference because it's the same supply voltage as before. Obviously if it's a higher supply voltage, rework out your resistor value just like we did in the previous one. That's all that you've got to do. You don't have to worry about anything else. So we want 10 milliamps to flow. That's the only thing that we have to worry about. Now how do you get 10 milliamps to flow? Well, IB is a question mark. We don't know what IB is. IC will be 10 milliamps. HFE will be dependent on the transistor that we pull out. Now then, generally for a transistor, say for the ZTX 448, it's quite a large value. It could be, I can't remember off the top of my head, it may be something from say 70 to 140 gain. Okay, it's very, very dependent. So we take worst case scenario and we say that HFE is 70, the absolute minimum, worst case scenario. So let's plug in the numbers. IC is 10 milliamps, IB is a question mark over, okay, and HFE is 70. So let's do the math. 10 milliamps. We want, what is IB going to be? What value do we need to multiply to get 70? Shuffle the numbers about, and we get IC equals IB over IB equals IC over 70. IC is 10 milliamps, and you can work it out. So 10 milliamps divided by 70. Right, back again. Had a slight problem there. Wasn't actually recording, so let's carry on. Right, so I've done my calculation, and IB works out to be, IB is up here, IB works out to be 140 microamps. Okay, 140 microamps, or 0.14 milliamps. So that's our base current. That's how much current we need to flow into the base to get 10 milliamps flowing down here. How do we get that amount of current? We've got 1 volt on input, 1 volt input. We've got 1 volt. We need 0.14 milliamps flowing. Use a resistor again. Resistors resist current. Okay, we can drop voltages, and we can work out our current working into the base using Ohm's law. Slightly different though, because we do get a base emitter drop. Okay, down here we do get our base emitter drop, and that's generally for a silicon BJT bog standard transistor is about 0.7 volts. So 0.7 volts drop across here. We've got our 1 volt input. That means that we're going to have 0.3 volts roughly across our resistor, across our base resistor. How do you work out resistance? Like I said, Ohm's law, V equals IR, our favourite old equation. We always go back to the basics. That's all that we need. So what we got? We got 0.3 volts over 0.14 milliamps. That equals 2.1 kilo ohm resistor. So this resistor is 2.1k. Big chunky resistor, very low current. Power rating is going to be absolutely piss poor, piss all. So 0.25 watt resistors, again what we've got hold of, perfectly fine. If you want, if you're purchasing your components, you can use a lower value again. Yeah, right. But yeah, do the math, you can work that one out. It's the same as before. And that's our little circuit setup. So here we scrub away all the junk, all the workings out. Get rid of that, get rid of that. A little bit there, let's a little bit here. Diddly diddly dee, diddly dee, diddly dee. Diddly dum. There we go. That's your circuit. Just resistor LED, which is the same as the previous circuit. And all that we're doing is adding in an extra resistor and transistor just to control voltages and currents. Easy. Now, the reason why I said we go for worst case scenario, 70 for the HFE as opposed to 100 or 140 HFE or anything like that, and it could be less if once we pull it out the component bag or whatever, is simply because of this. If this current, this gain goes up, then obviously if we've got only say 0.1 milliamps flowing in, well 0.14 milliamps flowing in, okay, and this was a gain of 100, we wouldn't have 10 milliamps flowing here. This will be 100 times greater. We'll have a ton more current flowing through here. But we don't have to worry about that. We don't have to worry about the gain increase because of this resistor. Your IC is worked out to be IC max. That's the maximum current draw that could possibly flow through your transistor. That's not the actual current that's been drawn, that's the maximum. That's up to the max. And we're actually limiting that amount of current using this resistor. So we're saying, yeah, transistor fully on, maximum current flow. Just use that resistor. Just like in the previous example where you got too much power. Okay, this is going to limit your current to what you need, and it's also going to drop the excess voltage from your supply across that resistor, so you only have the voltage that you need here. Now, some of you might be thinking, and some of you that know all this before says, you don't really need that resistor in there, you can get away with it. If you calculated this out to be 2.1k, you have 10 milliamps flowing down here. If only 10 milliamps flows, you're only going to get 1.8 volts drop across here, as long as across here. All the rest of the voltage is dumped across your transistor. Yeah, you can do it that way. The trouble is this HFE value. If this goes up, now you're going to have, an higher gain, higher current flow. High current flow means that you're gonna kill your LED. Okay, it's no good. It's no longer your 10 milliamps because you've got maximum current flow through here. It's useless. So it's all really, really good practice to have, your little voltage dropper resistor up here. In this case, sometimes it's called a current limiting resistor because you're actually limiting the current. So there we go, that's that. That's how you use your transistor to up your 1 volt to a higher voltage to turn on your LED if you haven't got enough power. And that's the same, if you haven't got enough current, you haven't got enough volt or voltage, either one or the others, that's the way to go. And not only that, you can use that same circuit if you do have a higher voltage, because you can put a higher voltage on the base, work out your currents going into your base and work out your IC and everything. Perfectly fine, and you're not going to blow out your LED either. But what's the point? What's the point in using that extra transistor and resistor if you've already got enough power? Let's face it, we like things easy, simple. Yeah, just use the single resistor with your LED. Now then, they're the two main ways of how to control your LED. Well, 3 if you include working your LED on a knife edge, as it were. You've only got enough power. The other way is, I'm just going to run through this on the quick, okay, because some people turn around and say, right, well you can control an LED if you've got too much power using PWM, pulse width modulation. Basically, pulse width modulation is, basically you've got a square wave, okay, and at the moment this is on for say 1 and off for say 1 second. This is what we call a duty cycle of 50-50, okay, or 1-to-1, a ratio 1-to-1, or 50-50, and so on, because they're even mark to space ratio. So mark to space, or it could be 1-to-1 or 50% duty cycle. Okay, what PWM is, what this basically works out to be is, if we take this as the equivalent DC, you get basically almost half power. You get an average. So if this was say 5 volts peak to peak, the average power would be actually 2 volts, the equivalent of 2 volts DC. So you could power your LED with 2 volts DC if you use a square wave. Okay, so plug in 5 volts, you get 2 volts drops across it, and so on. So you can use pulsed waves. PWM is basically this: you keep the frequency the same, but you change your duty cycle. Okay, so you have a short on and a long off. That means that you're going to have even less equivalent power. The average power is a lot less. And likewise, you can have it more on and less off, which means that you got more power, okay? Now, yes, you can do this. You can pulse width control LEDs. That's how you can dim an LED, and you know, you can get different light levels out of an LED. You know, without having to do much, you know, analog control. You can do it all in digital. The trouble with this is you have two scenarios to deal with. Either you've got your average power or your average voltage is going to be very, very low. This is going to be almost close to, say if this was 5 volts peak to peak, this is going to be almost, say, half a volt, 0.5 volts equivalent DC, you could say. So you take the RMS value, which is the average and what have you. I'm not going to go into the maths because this is just a quickie. And you've got another scenario where your pulses are on for a very long period of time and they're only off for a very short period of time. Okay, this is going to be almost maximum voltage, so you're almost permanently on at 5 volts all the time. 5 volts peak to peak. So this will probably average out to about, say, 4.5 volts, maybe 4.8. Well, you're in the same scenario as before. You've either got too much power for your LED to handle, or you've got too little power for your LED to handle. Yeah, not particularly good. If you're dimming an LED, you don't have to worry about the too little power because you want your LED to get dim. But you do have to worry about when it tends towards, you know, a permanent 5 volts, okay, because you've only got very, very small off times. So it goes back to the other two examples, okay, where you've got too much power. So you definitely want to chuck in your resistor again with your LED just to drop that excess power. Lots of people say no, you don't have to do that, you can get away with the LED, and PWM in the LED is not receiving full power. I can ignore that resistor, power it with the LED. It's perfectly fine if your mark to space ratio isn't going to go above the equivalent, you know, 1.8 volts DC for your LED. So, you know, you may only pulse width for up to an average of, you know, 1.8. So it might only be 30% on. And yeah, that's perfectly fine. But if your system accidentally, your microcontroller throws a brain fart or something, you know, whatever, and it starts outputting your marked spaces wrong, or your pin goes high for a long period of time, you can end up knackering out your LED. So it's always good practice just to shove that resistor in, and that's all I'm going to say about that, because it's all the same circuits all over again. And you can either use the transistor one, or you can use the, you know, just your bog standard resistor one if you actually want to. So, oh man, look at me hands, ink everywhere. Anyways, that's how you control LEDs. That's how you use them, and yeah, pretty straightforward. And yeah, I'll see you next time. Taxi tar.